So which is actually greener, a cloth diaper or a disposable one? It sounds like a pretty simple, everyday consumer question, right? Well, I want to ask you this right off the bat to instantly challenge your assumptions about what is truly eco-friendly. Because the truth is, the answer changes entirely based on the rules of your comparison. Are we just comparing the manufacturing of one single cellulose disposable diaper to one fabric diaper? What if we account for the fact that a child in fabric diapers might actually feel uncomfortable more quickly, meaning we'd have to compare one disposable to, say, 1.2 fabric diapers per day? And then you've got to factor in that the fabric ones are washed maybe 200 times over their lifespan. That requires hot water, electricity, detergent. Or what if our unit of measurement is simply keeping a child dry for their entire swaddling life? You see, the time frame changes absolutely everything. When you alter the mathematical boundaries of your comparison, you completely change which product actually wins. Welcome to this explainer. The real secret behind all that diaper mass? It's based on the blueprint of life cycle assessments, or LCAs. This is the rigorous, scientific standard we absolutely need to definitively compare the environmental footprint of products. And as we just saw with the diapers, it really is all about the math and the boundaries operating behind the scenes. Okay, here is our roadmap for today. We'll start with the LCA blueprint, then look at setting system boundaries, move into the functional unit, discuss handling added value, and finally wrap up with real-world LCA packaging. Section 1, the LCA blueprint, setting the rules of the game. Let's dive right in by defining exactly why an environmental study is being done in the first place and who it's actually for. The international standard sets a very strict rule here. It states that the goal and scope of an LCA shall be clearly defined and shall be consistent with the intended application. This is absolutely crucial. Before testing any product, researchers have to rigorously declare their objectives and their target audience. Why is this study even happening? Is it just for internal product tweaks, or is it a very public comparative assertion meant to influence government policy? You simply can't test things arbitrarily just to get the result you want. The rules of the game have to be set in stone before you begin. Section 2, setting system boundaries, drawing the line. So think about manufacturing a PVC window. The manufacturing process is deeply interlocked. You're looking at everything from oil and coal mining all the way down to extrusion and the final assembly. But smaller elements, like screws, Teflon foil, and fittings, sit intentionally outside the system boundary. Now, why would we exclude them? Well, if we're comparing a PVC window to a wooden window, and they both use the exact same screws and fittings, we can use what's called the black box method. We just omit those identical parts from the calculation to keep our analysis tightly focused on the actual material differences. When tracking multiple mass inputs into the production of a product, we really have to decide what matters before moving to downstream processes. We literally cannot track every single microscopic detail back to the dawn of time. It would make the math completely impossible. Now, what's really fascinating here is how the boundary explicitly tracks what enters from the Earth and exactly what exits it. On the incoming side, we track inputs straight from the environment, things like raw solar or fossil energy, and raw materials. And on the exiting side, we track exactly what goes back out into the environment as sewage, exhaust gas, and solid waste. Everything locked inside that boundary is considered the Technosphere. That's the world under human control. Since we couldn't possibly track every single atom inside that Technosphere, researchers rely on strict cutoff criteria to exclude insignificant inputs. The ISO standards highlight 3 primary metrics for this: mass, energy, and environmental relevance. Often, a rule is applied where anything contributing less than 1% to the overall system just gets cut off. But we have to be incredibly careful here. We can't just rely on physical weight to make that decision. And this illustrates exactly why. Take a hypothetical component 9. It accounts for a tiny, totally negligible 0.2% of the mass fraction. Now, if we only looked at weight, we'd cut it off and ignore it entirely, right? But wait, it actually requires 2.7% of the total energy. That is highly significant. And furthermore, if a material is highly toxic, it hits the environmental relevance criteria and stays inside the boundary, no matter how tiny its mass is. Section 3, the functional unit, the great equalizer. This brings us to the most critical component of our whole framework, ensuring we are always comparing apples to apples. The functional unit, or FU, is really the star of the show. It mathematically anchors the comparison so that products are judged by their exact performance, not just their physical item count. You don't just compare a bottle to a carton. You compare the specific, quantified job those items actually do. Let's look at a practical example from the source material, Floor coverings. Suppose we compare a thick plastic covering weighing 3.6 kilograms per square meter against a thinner plastic covering weighing just half that, 1.8 kilograms. The thin one takes less energy and material to make, so it's obviously greener, right? Well, not if the functional unit is defined as covering a floor for 30 years. Because if the thick plastic lasts 30 years, but the thin one only lasts 15 years, the math dictates we have to measure 2 of the thin coverings to satisfy that single 30-year functional unit. And just like that, the heavier, thicker product is actually the far more sustainable choice. Section 4. Handling added value. Balancing the scales. But how do we handle situations where 2 products don't fulfill the exact same function and one has a distinct added benefit over the other? We use a brilliant concept called system expansion. Say we're comparing 2 ways to dispose of 1 ton of municipal waste. System A is an incinerator, and System B is a basic landfill. Both successfully dispose of the waste, but System also generates electricity from the heat. To make this a truly fair comparison, we actually have to expand System B. We must add the environmental burden of generating that same exact amount of electricity to the basic landfill side to balance the scales. We absolutely have to ensure we're measuring equal benefits. Section 5. Real-world LCA packaging. Putting it to the test. Let's pull all of this methodology together and observe how this framework operates out in the wild. The question posed to researchers in a major European study was, which is the ecologically favorable choice, PET single-use bottles or beverage cartons? Now, this wasn't just some academic exercise. A German packaging ordinance had sparked a massive industry debate by exempting beverage cartons from mandatory deposits specifically on ecological grounds. To resolve this, researchers conducted a rigorous LCA to definitively and impartially compare the different packaging formats against PET bottles in the real world. To avoid arbitrary results, those researchers had to lock in highly specific functional units. They matched market-relevant segments volume for volume, literally down to the exact milliliter, ensuring an absolute apples-to-apples comparison. We're talking about things like storing exactly 1,000 to 1,500 milliliters of fruit juice in a carton versus the same exact volume in a PET bottle. Or 500 milliliters of fresh milk for instant consumption. It perfectly anchors the comparison purely around the performance of the packaging. By carefully drawing these boundaries, the goals of the study were achieved. The resulting data gives manufacturers a clear mathematical roadmap to optimize their packaging designs. But maybe more importantly, it promotes object-driven dialogue. It gives policymakers and consumer organizations hard, objective facts instead of relying on political guesswork or just gut feelings about what looks greener on the shelf. So, declaring a product eco-friendly is entirely meaningless without understanding this blueprint. True sustainability isn't just about the raw material you hold in your hand. What really defines environmental impact is where you draw the line, how you define the functional unit, and how you do the math. The next time you grab a product off the shelf, whether it's a baby diaper or a carton of juice that claims to save the earth, I want you to ask yourself, what exactly are the mathematical boundaries of the claim I'm buying into? Because in the complex world of sustainability, it's not always the material that saves the planet. It's the math.